Good afternoon, or I should say good morning, ladies and gentlemen. Welcome to Yokogawa's analytical web seminar called Basic Conductivity. We would like to thank you for taking the time to attend, and we hope you find this seminar helpful and informative. Before we begin, we would like to go over some housekeeping issues. The audio part of the seminar is accessed either through the teleconference number provided in the Info tab of your WebEx Manager window or through your PC speakers. To hear the audio through your PC, if you can't already, select the Communicate tab and join the audio broadcast. The seminar will last approximately 1 hour. Towards the end of the presentation, where time permitting, we will have a question and answer section where our featured speaker today will answer some of the questions received from the audience. If your question is not answered during the presentation, please be assured that we will answer them directly via email. All questions should be submitted in either the question and answer window or the chat window located in the lower right-hand corner of your screen. Today, our featured speaker is Nick Nichols. Nick is the Liquid Product Manager for Yokogawa, and he has been with Yokogawa for 25 years. Prior to working with Yokogawa, he worked 18 years at Rosemont. We would like to get the seminar started by handing it over to our featured speaker, Nick Nichols.
Again, I'd like to welcome everybody for joining us. This is the second session this year for this topic, and we are recording it, and it will be put on the website for those of you that find it useful and want to refer back to it or recommend it to others who come and view it. Our goal for this webinar is to gain a practical understanding of the strengths and the limitations associated with the measurement of conductivity of an aqueous solution. We'll explain what the differences are in measuring the conductance or conductivity, resistivity, or the percent concentration of the process in question. We'll cover the type of equipment required, contacting or inductive, in order to obtain an accurate and reliable measurement. And we'll discuss what the cell constant or cell factors are with a sensor and their importance in making the measurement. We'll also take a look at some typical applications where conductivity is most often used. Throughout the presentation, we're going to touch on some of the typical problems encountered when measuring conductivity and a few troubleshooting tips that can be used to solve them. Typically, conductivity is preferred over other measurement parameters because it's less costly and less maintenance intensive. With that in mind, let's start out with a basic definition. In an aqueous solution, conductivity is defined as the measure of a solution's ability to carry or conduct an electric current. An electric current will flow through certain solids and liquids when a voltage difference exists between 2 points. For solids, such as copper wiring and printed circuits, the current flow is achieved by electron charge transfer through the atomic structure of the material. For liquids, the mechanism is different. The presence of ions, or charged particles, represented by the colored dots in the diagram, they're necessary as they are the carriers of the current flowing through the solution. If there are no ions present in the liquid, such as with ultrapure water, then no current can flow and the solution is not conductive. As an example, if you had your house set up to where you were able to bring in ultrapure water instead of just regular city water, and you happen to be taking a bath in that ultrapure water, and your spouse accidentally dumped the hairdryer in with you, and it was plugged in, nothing would happen. Other than you get the blow dryer wet, it probably wouldn't work anymore. However, if the water is not ultrapure, which is what we typically have, it has some conductive material in it, and there are ions present, current would flow, and your spouse would probably be reviewing the benefits from your life insurance policy. The basis for measuring the conductivity or conductiveness of a liquid begins with a formula known as Ohm's law, shown in the diagram. This states that the amount of voltage in a circuit is the result of the amount of current multiplied times the amount of resistance in the circuit. Since we are interested in how well the circuit conducts that current, which is determined by how much resistance to the current flow there is, we must rearrange the equation to find out the resistance value by dividing the voltage by the current. Once we've figured out the resistance, it's an easy matter to determine the conductivity, as it is simply the reciprocal or inverse of resistance, and is shown in the third equation where G represents conductivity. There are two basic approaches for measuring conductivity that are determined by the type of sensor used. There's contacting and inductive, or non-contacting, which also is referred to as toroidal or electrodeless. The contacting method, as the name implies, uses a sensor with 2 or 4 metal or graphite electrodes which are actually in contact with the solution. It is represented by 2 plates on either side of the solution in this diagram. An inductive sensor, on the other hand, has 2 toroidal coils, a driver and a receiver, sort of like a transformer, that are encapsulated within an inert material such as PEEK or Teflon, for example. And that material protects the coils from the process. And we'll talk about both of these sensors more as we move along. Here's the scale to give us a visual of the relationship between conductivity and resistivity. Once again, we see that conductivity is simply the reciprocal or inverse of the resistivity or resistance of the process. If a loop is highly conductive, then it is low in resistance to current flow, and if it's and vice versa. If it's not very conductive, it's high in resistance. The engineering unit used to represent resistance or resistivity is the ohm. The engineering unit of measure for conductivity is the Siemens, but you'll also find the term mho used, M-H-O, which is simply ohm spelled backwards. Mho and Siemens are treated the same when you are making conductivity measurements. So if someone calls and says, I have a range of 0 to 100 microsiemens, that's the same as a range between 0 and 100 micromhos. It's the same thing. From the example shown on the scale, we can see that conductivity ranges from very low values, theoretically pure water around 0.055, 0.057 microsiemens, to very high values, which are several 100,000 microsiemens for acids and caustics, as the concentration of the conductive ions increases. Remember, the amount of ions present in the liquid relates to the level of conductivity measured. There's a question, if you have a pure or ultra-pure water applications, such as in power plants and computer chip manufacturers, some companies prefer to use resistivity of the process rather than conductivity, or vice versa. What would be the reason? The answer simply is preference. Some prefer to read very large resistance numbers, 15 to 1800 megohm, instead of very small conductivity numbers, 0.05 microsiemens. However, the result's the same. It's just 2 different ways to look at the same measurement. Another key industrial use for conductivity measurement besides pure water is for processes with much higher conductivity values. Here we are determining the chemical strength or percent concentration of a solution. There are 3 factors we need to pay attention to in order to successfully make this type of measurement. The first, that each chemical responds differently from the next with regard to its conductivity value versus percent concentration level. Often the difference is significant, but sometimes it's not. These differences have to do with the size and mobility of the ion of each chemical. The second factor to consider is that the conductivity is nonspecific. It is a nonspecific measurement. And the third factor is that the temperature affects all conductivity measurements. And we're going to see this over and over again, that temperature affects your conductivity measurement. So it's very important to have control over what you're seeing with regard to temperature. The first factor, which was that each chemical responds differently from the next, is illustrated on the graph, where you can see the effect of different sized ions of each chemical reflected in their different curves for conductivity versus concentration. For the 4 chemicals shown, they are all different. This points out how important it is when we set up our analyzer that we put the correct curve information in for the specific chemical we're measuring, or our results are going to be useless. And many analyzers have built-in tables for conductivity values versus concentration to select from, and also a capability to build your own. So this should be an easy task. We just have to make sure that we have the right one in there, or the values we get out are not going to mean anything to us. You'll also notice that at a certain point, the continued rise in the percent concentration results in a decrease in the conductivity value. This is due to the increasing number of ions in the solution beginning to interfere with one another, causing the mobility of those ions and therefore the conductance of the solution to decrease. This change in direction could be a problem if the measurement range that you happen to be including goes over where that curve peaks out and begins to decrease, such as between 18 to 50% sulfuric acid or 10 to 30% hydrochloric acid. As you can see, the problem is there will be one conductivity value that represents two different percent concentrations. At 18 and 50% sulfuric acid, the conductivity value is about 600,000 microsiemens. So just reading the conductivity will not tell you what the percent concentration is that you're measuring. You also need to know which side of the curve you're on. Now, the simplest solution to this problem would be to make sure that the range you set up never crosses that peak point. However, there may be occasions where that's not possible. So what do you do then? Well, it becomes a little more difficult, but using two analyzers and a secondary device such as a flow meter to validate which side of the curve you're on, and a way to switch the output from the first analyzer to the second one once the peak is reached is a way of doing this. The second factor that we need to consider is that conductivity is non-specific. Sometimes the size of the ion of different chemicals and the way they relate to the conductivity are similar, so you have to know what you're measuring because a conductivity measurement only tells you the conductivity, not what the solution is. This is very important. As the graph shows, you can see the actual conductivity value of various percentages of sulfuric acid, that's the red line, and sodium hydroxide, that's the blue line, are very nearly the same. For example, a 4% concentration of sulfuric acid is approximately 179 millisiemen, and a 4% sodium hydroxide is about 185. So just knowing the conductivity is not really going to tell me what I'm measuring. So in cases like this, at lower concentration levels, a pH instrument could also be used as an indication telling you whether it happens to be an acid or a base. When you get into higher concentrations, pH is no longer something that you could use, so you have to find another way to know what it is that you're measuring, but you do need to know what's in there. Finally, the third factor we must consider is the temperature of the solution. As the slide reminds us, the mobility of the ions in the process affect the conductivity values we will see. The higher the concentration of any solution, up to a point, remember the curves we looked at earlier, the higher the conductivity value. Again, the type of ion also directly affects their mobility. The hydrogen ion, for example, is smaller and more mobile, and therefore more conductive than a larger sodium ion. That is why their curves are different. Temperature also affects the conductivity measurement. As the temperature of any process increases, it affects the mobility of the ions, causing them to move faster, resulting in a false higher conductivity value. Because of this fact, all conductivity sensors include a temperature element of some sort to compensate the process temperature back to some standard reference temperature, usually 25 degrees C. Without this compensation, any temperature change would appear to us as a change in the conductivity value. And it would be false. It's a temperature change, not a conductivity change. In some pharmaceutical applications, it is desired to measure uncompensated conductivity value as alarm set point for impurity levels. But this value is not really practical for process control. We need to have temperature control in order to have an effective measurement. All right. Before we go on, let's take a quick review. Conductivity is defined as the measure of a solution's ability to carry or conduct an electric current. For aqueous solutions, ions are necessary to carry the current. No ions, no current. An increase in ions reflects an increase in conductivity up to a point. Remember when we reach that peak and they begin to slow one another down and the conductivity decreases, but the percent concentration increase. And in addition, the size of the ions affect the mobility and the temperature of the process. Simply put, we must be able to accurately measure the ions in the solution, know when they are beginning to interfere with one another, and eliminate the effects of temperature would have on the process if we are to get a usable measurement. All right, How do we do that? Let's start with the basic equipment required for a typical conductivity measurement loop. It includes first an analyzer or a transmitter of some sort to convert the sensor signal to a 4 to 20 or other output that's usable for control or monitoring. And we also need an interconnecting cable to mate the sensor to the electronics, preferably, obviously, a noise-free cable, so a very well-shielded cable so that we don't have any interference outside of the process. Then a sensor, which is typically either a contacting or an inductive style, and we'll discuss the differences in a little more detail as we go on. And finally, we need some way to get the sensor online, such as a holder, like a flow-through version shown in the slide, or some other type of process connection. That's pretty straightforward, pretty simple. As we've mentioned a couple of times previously, there are two common sensor designs currently used for conductivity measurements. It's contacting and inductive, and inductive is also known as toroidal or electrodeless. And the key differences to consider when deciding which type of sensor to select are maintenance and accuracy. The contacting style sensor gets its name from the fact the actual measuring electrodes are in direct contact with the process. As a rule of thumb, contacting sensors are most reliable and require the least maintenance when they're used in low conductivity applications, such as pure water applications in power plants and computer chip manufacturing. Don't misunderstand, contacting sensors can be used for applications with high conductivity values, but problems of material compatibility, coating, and corrosion increase the maintenance they require and their life expectancy. Inductive sensors do not have any measuring element that comes in direct contact with the process, and therefore they do not suffer from coating or corrosion problems. However, they are typically less accurate at lower conductivity values than contacting sensors are. Let's take a closer look at the two types. First, contacting. Since we're interested in the measuring conductivity of the solution, the exact volume between the electrodes becomes very important. It must be well-defined and repeatable to be of use. Otherwise, we're not going to be able to tell whether the changes in the current flow we see are due to the concentration change in the process or just the random repositioning of the measuring electrodes. This volume between the electrodes of the sensor is defined by what is called the probe or cell constant, and determines what the effective measurement range of the sensor will be. The basic probe constant of 1.0 is defined as two 1-centimeter electrodes separated by a distance of 1 centimeter, as shown in the slide. The cell constant is calculated by dividing the distance, the length between the two measuring plates, by the area of the plates. Now remember, we're measuring the current between these plates, so we want to keep that current at a level where the analyzer can measure it most effectively. If we increase the area of the plates and shorten the distance between them, more ions will be able to travel to the plates and make contact. That's why we use small cell constants in low conductivity solutions that have low concentrations of conductive ions. It ensures that the current between the cells is at a level high enough that we can measure it accurately by the analyzer. The raw conductivity value is then multiplied by that cell constant, which is why we see the unit microsiemens per centimeter. In solutions with high concentrations of conductive ions, we want to do the opposite. We want to decrease the area of the plates and increase the distance between them. This ensures that the current flow is low enough that we can measure it accurately. This is why we choose cell constants of 10.0 or higher for highly conductive solutions. The key is knowing your measurement range and picking the correct cell constant to match. What happens if the wrong cell constant is selected, or the process conductivity actually increases for some reason? In either instance, something we call polarization will occur, rendering the measurement useless. In the slide, you can see in the first example titled Normal Operation, a solution which the correct cell constant, where the ions are free to travel from one plate to the other, effectively carry the current. The second example, titled Polarization, shows the same cell constant being used in a highly conductive solution. When the voltage alternates, switch polarities, the ions cannot freely move to the other plate because the ion density is too high. This results in less ions contacting the correct plate, which will result in a false low reading. The electrodes effectively are polarized. So how do we prevent this? Well, first off, always select the correct sensor cell constant. Increase maintenance to clean the electrodes if you're in a solution where highly more conductive and these can build up on the electrodes because that's covering some of the surface area, which will lead to this problem. Or you could use inductive sensors. Okay, let's look at the inductive style sensor. Some of the obvious benefits over contacting style sensors are that no actual contact with the measuring elements and the process occurs. Therefore, inductive sensors are not as affected by coating or corrosion and will not polarize like contacting types. However, to be fair, should that hole in the donut there become plugged, it will stop measuring correctly. Inductive sensors typically have a wider measurement range than contacting, but as we mentioned earlier, they are less accurate at low conductivity values. So the rule of thumb, below about 50 microsiemens is where you would want to use a contacting sensor instead of inductive. Also, attention needs to be given to the material of construction. Inductive sensors are available in a wide variety, such as PEEK and Teflon. PEEK for the most common measurements, and usually Teflon for high chemical concentrations of chemicals such as sulfuric acid. Okay, how do they work? Well, their operation is based similar to how a transformer works. When a voltage is applied to a coiled wire, a current flows through it and creates an electromagnetic field. This is what is done at the drive coil shown in the diagram. Conversely, an electromagnetic field will create or induce a voltage in a coil that is exposed to it. This is what happens at the pickup or receiver coil. The strength of the electromagnetic field and consequently the strength of the induced voltage at the receiver is dependent on the conductivity of the liquid passing through the two coils. So, by measuring the voltage received at the pickup coil against the voltage supplied at the drive coil, we're able to determine the conductivity of the solution passing between them. While inductive sensors have a great many advantages over the contacting style, they do have some limitations we need to pay attention to. The inductive sensor has a cell factor, which is somewhat similar to a cell constant on the contacting sensor. Typically, the inductive sensor cell factor can cover a much wider measurement range than is possible with a contacting style. But you must be sure that this value is entered properly into the analyzer as it acts like a cell constant and directly affects the accuracy of the reading. Because the inductive sensor works by creating electromagnetic lines of flux, these can be interfered with if the donut portion of the sensor, where the coils are located, is installed too close to the pipe or tank wall. This interference will change the effective value of that cell factor, as the graph shows above. There are two ways to address this issue. Obviously, the first would be to make sure there is sufficient distance between the sensor and the process walls. This is usually about 1 inch all around, but check with the manufacturer just to be sure. The second, which is a kind of benefit, is that you can do a calibration with the sensor installed, and the effect of this location will automatically be corrected and the cell factor adjusted for the analyzer. In other words, you're calibrating it to the particular location that it's in. Now, it's not always easy to calibrate in place, but it is a solution for applications where there's not another choice for the sensor location. Okay, let's have another quick review. Contacting electrodes come in direct contact with the process. They're affected by coating or corrosion, and they will polarize if the wrong cell constant's used or the conductivity of that process happens to increase. It does require additional maintenance if you're in higher conductivity solutions, but the least maintenance is in pure water applications. For the inductive sensor, there's no direct contact with the process for the measuring components. It's corrosion resistant, will not polarize, but you have to keep that hole cleared, or because if it's plugged, it will not read correctly. And attention needs to be given when you mount it, or proximity to the tank wall or pipe wall. What material am I required to use for this particular process? And when I have it installed correctly, relatively there's no maintenance at all involved, which is a big advantage. To make it simpler for everybody, here's a brief guide I use when I'm considering either one of these styles. Basically, for low conductivity, 5,000 microsiemens or less, I'd use the contacting style. Above 5,000, I would choose inductive. Of course, there's a great deal of latitude in making this choice since contacting sensors have been used successfully for many years in high conductivity applications, and also inductive sensors can be used down to somewhere near 100 microsiemens effectively. So it's a trade-off as to which you want to use, but as a rule of thumb, this will give you a little bit of a guideline to start from. Why do we choose to measure conductivity rather than some other parameters, such as pH or maybe dissolved oxygen? Primarily because it's less expensive and requires less maintenance and calibration than other parameters like pH. Conductivity can be used in a variety of applications, from pure water, as we've talked about today, through percent concentration measurements. But basically, it's a simpler measurement to deal with regard to installation, maintenance, and calibration. Here's a list of some of the areas where conductivity is used, and you'll notice that pH is also used in many of these applications as well. And often these two parameters are used together for measurement and control, such as in cooling tower or boiler feed water or boiler blowdown applications. Once again, the two most common uses for conductivity measurements are to determine and control the relative purity of the water, or to measure the percent concentration of a specific chemical. Now, we skirted around the issue, but what kind of maintenance is actually required for conductivity loops? Basically, it's a one-point calibration. We need to initially calibrate that sensor, the entire loop, and depending on the application, the frequency of recalibration is usually determined by the plant. If it's an application where cleaning is required because it's a higher conductivity solution, then we're using a contacting style sensor. Some industries require annual maintenance regardless of whether everything's functioning correctly or not, just that the proper documents can be given to Uncle Sam to make sure where everything's being done right. It's a simple one-point calibration using solutions that can either be purchased commercially or made up in your lab. And there's also air calibration that can be done, which effectively zeroes the sensor. And this is a one-point calibration. We're not doing like we do for pH, looking for zero offset and slope. It's merely calibrating this sensor to the process. A little closer look at some of the applications. This graph shows the significant advantage of using conductivity versus a manual or a time method for boiler blowdown control. You can see how tight the control is by measuring the conductiveness of it, as opposed to just turning something on, blowing it down for a period of time, and then shutting it off. You can see in this pure water drawing here that conductivity, all the little conductivity labels in there, that there's quite a wide variety of application sites for conductivity in pure water applications in a power plant. Due to the chemical content, coating, and potential fouling issues in a pulp and paper plant, inductive conductivity is ideally suited for this application. And you can see that it's shown there in a number of different places. As a summary, what do you need to know? Selecting the proper equipment for a conductivity application is not really that difficult. You need some basic information as listed on the slide. You need to know your measurement range, You need to know chemical compatibility, installation requirements, physically how am I going to get this online. And once you have this information, you can talk with your vendor and they can easily work out with you what the right product happens to be for your particular need. All right. If there's any questions?
Thank you, Nick, for that presentation. Let's go ahead and we'll take some questions here. We're using conductivity to control specific gravity of our fluid. Is there a relationship between the two?
That's a good question. I know that we have relationships between TDS, but I'm not sure specifically what the relationship would be with specific gravity. It depends, I think, on what chemicals it is that you're measuring as well. But I'll do a little research on that, and we have be able to answer directly to you what I find out on that.
What is the difference between a 4-contacting electrode and a 2-contacting electrode?
Basically, 4-contacting was a movement from the early days to allow us to have a sensor that works in higher conductivity applications that would be affected much less than the 2-electrode as far as polarization, because I have 4 electrodes and it gives me a larger surface area, and also the configuration can be arranged where some of the electrodes are a little more protected, but it's basically was used to allow me to measure with a contacting style sensor in higher conductivity solutions with less maintenance requirements.
How can I be sure for my range that I've picked the right cell constant?
Well, that's where you need to discuss it with your vendor, because depending on the vendor, there's some changes. As an example, in our area, we have basically 4 cell constants: a 0.01, a 0.1, a 1.0, and a 10 for the contacting style. And the reason we only need 4 is that due to our electronics, we are able to measure a wider range with a particular cell constant. Other vendors may require that, depending on their electronics, they may not have as wide a range. So let's say you're looking to measure between 0 to 10,000 microsiemens. We may be able to handle that with one sensor. They may say that you need a different sensor with a different cell constant because of their electronics. So it's basically you need to talk with the vendor to find out, here's my range, what cell constant with your equipment do I need in order to measure that range? And it may be slightly different from one vendor to the next.
Okay. Do you know where I can get information like the graphs you showed for percent concentrations?
Yes, we do have, and they'll be out on the a website at some point, a list, I forget how many pages it is, where it is a wide variety of chemicals and percent concentrations, all referenced to 25 degrees C. That was one of the graphs. I think there's something like 15 or 20 of them, but we'll put that out on our website if it's not already there. So you would have access to downloading that so that you could use it.
When we measure low conductivity values below 100 microsiemens, what is the best reference for calibration?
Typically, there are some stable solutions that are at 100 microsiemens, and that would be the one I would use. The sensor itself, once you've calibrated it effectively, I'm talking about a contacting style now. You've calibrated effectively, and now you're measuring in low conductivity water. You don't have to have the calibration fluid in the area that you're trying to measure. You want something that's stable so that you're accurately calibrating the sensor. And about 100 microsiemens is the lowest you can go, because once you've opened the solution, any evaporation is going to change the value of that conductivity solution. So to get one that's a very low conductivity is difficult. Now, there are some. I'm familiar with one from Hamilton that's a very low conductivity, but the idea is to find one that's reliable. If you're making your own and you're using standard salt solutions, about 100 microsiemens is the lowest I'd go, but it will still allow your sensor to measure very accurately at lower levels. It's just that you can't find a solution lower that's going to be accurate and stable for very long. Again, Hamilton does have one, I believe, so you might want to investigate that.
How often do I have to calibrate?
That depends, one, on the application, two, on the customer. In some power plants, some pharmaceutical plants, and some chip manufacturers, they have a PM set up to where they're going to calibrate X number of months or annually, and it's set up whether it's required or not. For pure water applications, you really shouldn't need, unless there's some sort of a spill or something going on that's out of the norm, annually is probably sufficient, because all you're going to be calibrating for is any effect on the actual elements of the sensor itself. For high conductivity solutions, if you're using contacting, it would have to do with whether they were becoming coated, and that's sort of empirical. You have to see how the application affects it, and then set up your maintenance time accordingly. If you use inductive, once you've calibrated in place, just to keep, so for peace of mind, you might want to check it annually, but really there's nothing that can coat it or affect it, so it's really not required to be recalibrated that often.
How do I know if my sensor has been polarized, and if it has, what do I need to do?
If it's been polarized, it's one of two things. You have put in the wrong cell constant for this particular range, or your cell constant was correct, and now the process has changed. You're going to get a false low reading. You're going to see something that doesn't look like it should, and most of the equipment today will give you an alarm that says, I'm not getting the proper current flow through here, the electrode are being coated, something's not wrong, and it'll give you a flag that it's been coated. You can pull it out. If it is that the process has changed, then there will be some coating that's occurred. Clean the electrode, and you'll be able to put it back in. However, if the process has changed to the point where now this particular electrode is the wrong cell constant, then you're going to have to change electrodes. But typically it's because there's some sort of a spill or an upset or something that's gone on that's come through the line and it's coated the electrodes, and now you're going to get an error code and a false a low reading that is going to require you to clean the electrode and check to see what the cause of this particular error or breakthrough is, where it came from.
Do all sensors with a 0.01 cell constant give me the same measuring range?
No, it depends again on the electronics it's matched to. One manufacturer may say you'll get 0 to 500 microsiemens. Another will say you'll get 0 to 2,000. It depends on the manufacturer and their electronics, and that's why it's matched to the loop when you do your calibration. Because many sensors, in fact, I know our equipment for certain can use other vendors' electronics. Can use other vendors' sensors, but that the range that we can obtain would be different than them using that sensor with their electronics. So it's a matter of meeting the two together and finding out from the vendor what they say their range is.
Okay, now we have our last question here. It's a little detailed. Customer was wondering if there has been technology similar to what you see with ultrasonic flow meters, where an inductive sensor has been designed that it can be strapped to a pipe with a given pipe material to determine what the conductivity of the fluid is.
There is a toroidal version that has a built-in tube. I think Emerson has one. So there is a way to take the toroidal basically, and there's a pipe built in with flanges on either end, so you can mate it there. But the device is outside the process. It's around the pipe. But that pipe, in all honesty, is actually part of the sensor. So what you're describing, where you could just bring something and clamp it on, that's being looked at, but there is nothing that exists today. Today, it's you have to have a physical piece that's cut of a certain length, and the coils built around it. So the coils are outside the process, but still that length of pipe is part of the measuring loop.
Thank you, Nick, for taking some time to answer some questions as well as the presentation that you gave to us. Again, we'd like to thank everybody for attending and participating in the online web seminar. We would like to mention that this seminar was recorded and will be available for replaying in 24 to 48 hours under the technical library of our webpage. We hope to see you online in our future web seminars.